Okay, welcome back, everybody. We're going to pick back up on another lecture. And in this lecture, I wanted to clarify some points and really show some of these characteristics and important variables that fall within this logistic map. Now, you might ask, why am I spending so much time on this map? Well, this map is fundamental to how a lot of chaotic oscillatory flows react, and you'll see as we begin to make some progress, you'll see how we relate these maps to these continuous time flows, and how then you can kind of bring some of these same measures back to bear, and why those measures are then relevant to what's going on in that continuous time system. Okay, so we're gonna go back and calculate some things. I think I kind of made a couple of mistakes I want to clarify the last time. So we're going to go back. We're going to again figure out what the apex is for the map given different values of this specific variable rho, and then we'll look at the fixed point, make sure we calculate that properly. We're going to walk through the estimation of the Feigenbaum number, and I'll try to actually walk through you with it in MATLAB so you can do the same thing. And then we also are going to do some estimations of the Lyapunov exponent. And if we have time or the inclination, we may even see if we can discuss the fractal dimension of this bifurcation diagram that comes out of this logistic map. So let's just start in the first place. So as you remember, this is the equation, and I went ahead and said, let y equal x of n plus 1, and I let x equal x of n. So that way now you can write this as y equals rho x times 1 minus x, which equals to rho x minus rho x squared. And now, so let's remember that. I'll go down here so we can do some work. So again, we have y equals rho x minus rho x squared. So we want to first find the apex, and that is, the point where the peak resides. That's the apex. Where is that? We call it x. What did we call it before? I'll just call it x of a since we called it apex. What is that value y sub a for any value of rho? All right. Well, so what you're doing, the reason why we take the first derivative and then find where it's 0, because this as you go up, this slope is high and it's positive. When you go down, this slope is negative. But at the peak, especially if you have a single humped map, at the peak, the slope is 0. So you're trying to find that point. Well, how do you find the slope? Well, that is the continuous time derivative. So we're going to set dy dx, the change in y with respect to x, equal to 0. So if I differentiate that, dy dx equals row, because that goes away, and what the mistake I made last time was I forgot the 2. So you have 2 row x. Okay? Now, when you set that equal to 0, you now have row times 1 minus 2 x equals 0. So the row goes away. You have 1 equals 2x, and therefore x equals 1/2. So no matter what the value of row is, the peak is going to always be at the point of x equals 1/2. Now you can go back. So now we have x of a, we called it, is equal to 1/2. Now you can go back and put that in and say ya, that's this point, is going to be equal to row xa minus row xa squared, which this is row times 1/2 minus row times 1/2 squared, which is equal to row over 2 minus row over 4, which is going to be equal to 2 row minus row over 4, right? Which is going to be equal to row over 4. Okay? So that's the value at this point. Okay? Well, let's do our sanity check. We've played with this already, and we can go back here. So at these points, we said that the value is that ya equals row over 4. So we can see very clearly that for 4 row equals 4. Well, let's just do the table right here. So for row and ya, when row is equal to 4, that's clearly 4 over 4, but that's 1. And that makes sense because that's your point right there. We can say 3, we've got, then that's 3 over 4, or 0.75, and you can see that that clearly falls somewhere right there. And so on. For 2, row equals 2, that's going to be 1/2, and that's where you have your peak there, and so on, right? 1/4 is, yeah. So for 1 is 1/4. All right. So that's the apex value, all right? Now, the next thing is this fixed point. Here we are again, y. The fixed point is where does this intersect with the y equals x line. This is the y equals x line right here, runs through there. Where does this map intersect? There's this point. This one is trivial. This should be, you know, y equals x equals 0. That's a trivial point. But this is the one we're looking for. So how do we find that? Well, again, we're going to just say y equals row x times 1 minus x is equal to x. Where is that point? And then we're going to solve for that point. And we'll call this point xf for fixed, and that'll be yf for the fixed point. Now that's something that's going to move with respect to the value rho. As we change rho, the fixed point will change. So let's see if we can figure that out. All right, so we'll say this is equal to, or we'll just say, let me just get rid of that. So we'll say rho x minus rho x squared equals x. Okay. Now, you know, I shouldn't have did what I just did, because I could have just canceled the x's out. So if I go back up here and do that, cancel the x, you should have rho minus rho x, okay, doing that multiplication, equals 1. All right, so we're solving for x, so now I'll move that over here and move that over there to keep the signs. So that's rho x equals rho minus 1. And so xf, the fixed point, is equal to rho minus 1 over rho. All right, so that's all dependent upon rho, but as you can see, it changes the position. So let's do this table again and see if we can figure out some of our values. So let's go with rho equals, we'll do 4, we'll do 3, we'll do 2, we'll do 1. All right, and xf, and maybe even do yf, because we can always use MATLAB if we have trouble calculating it. All right, but let's do xf first. All right, so if we say that's 4, we have 4 minus 1, which is 3 over 4, so 3/4. Okay? Then we have 3, so 3 minus 1 is 2 over 3, and we have 2/3. And then 2 minus 1 over 2 is 1/2, and 1 minus 1 over that is 0. Okay, so we have these points for x, and of course we can plug that into y to get y of x. Instead of trying to be a mathematical genius, I'll just let MATLAB do the work for me. So we're going to use, let's just say xf equals, no, let's do this. Let's say r equals 4. Okay, then we're going to say xf is equal to r minus 1 divided by r. And as we can see, that's for r equals 4, it's 0.75, as we said. Now we're going to put it into the expression. We'll say yf equals r times xf times 1 minus xf, and I'm going to see what that is. And it turns out that that is also 0.75. Well, guess what? It should always be the same value because it is the fixed point, right? So that's what I didn't want to tell you. But it should always be the same, 3/4, because that is the point where they're equal. Okay? You know, if we had been sitting in class, I'm sure one of you would have raised your hand and said that. But let's just, you know, do it again just to prove to ourselves. So now we can just go up, right? So now I'm going to say r equals 3, and I'm going to say the same thing for that. So now you can see it's 2/3, which makes sense. And then we're going to go to YF and see that's also 2/3. Okay, so now we know, well, let me just put 2/3. So now we know, we've proven that we found the right formula for that, and that is this. So that is your fixed point. Now, interestingly, what you'll see on the map, the bifurcation diagram, if you remember, and by now I'm sure you've gotten comfortable saying this word, bifurcation diagram. The fixed point kind of runs in this way. And as you see R or rho in this case changing, that fixed point changes as well. And at 4, at 0.75 is probably right around here. And so that fixed point is running through here. Now, interestingly, the map doesn't always live at the fixed point, okay? There are places where it does not like the fixed point, but in these more heavily populated regions, the map visits the fixed point, but it doesn't stay there. This back here, beyond 3 and others, are the places where it tends to stay before it bifurcates into these 2 points and then these 4 and so on. Okay? But the fixed point kind of lives like a ghost within this bifurcation diagram. Now, what we also wanted to do was to begin to estimate where this Feigenbaum number is. And so this is the way you calculate the Feigenbaum number. Now, what you see here is you need 3 values on the bifurcation diagram. You need this value, let's call that row 2, since that's where it splits into a series, double. It doubles right here. It splits into 2 periods right here. This point, which should be the same points, would be row 4. So let's call it row 4. Now, again, it doesn't matter what these numbers are right here because it's the next one and the next one. But since it's a period doubling, we're going to call it 2, 4, 8, and so on. So this would be 4, right? I mean, sorry, 8. Because this is where period number 8 begins. And so what we're going to do is, use MATLAB to calculate the diagram and then zoom into it and try to figure out where these values are. Now, while we're talking, what I should have done was run this for many more iterations. So I'm going to do that. And I'm going to, instead of 1,000, I'm going to say 5,000 points between those steps. We're going to start right where we know. So right beyond 3. Just before 3. I'll go back and change that so that we can look at. So we're going to, I'll say 2.95. we don't need to go all the way to 4. So the smaller we make the window, the more we can see inside of it. So let's just say 3.7 in this case. All right, so we're going to go from 2.9, let's say 2.9 to 3.7. We did 5,000 iterations per, but also 5,000 steps. And I'm not really sure how long that'll take, but I'm going to see. And hopefully by the time I stop talking, you'll see that. Now, so we can figure out where these, so this will be, the row value for where this splits minus the row value for where, no, it's actually backwards, so the higher number. So the row value where this splits minus the row value where that splits over the row value where this splits minus the one where this splits. Okay, so more specifically, it's going to be row 8 minus row 4 over row 4 minus row 2. Okay, so while we're waiting, we'll make our table. We'll just say, well, I'll just write row 8, row 4, row 2. And I'm going to, hopefully when this finishes, I'll be able to, and it did finish, yes. So we're going to just make this bigger. We're going to zoom in as much as we can on these values. Well, and we're going to click on that. So in this case, X is the row value, R value. So that one is 3. So for 4, I'm sorry, for 2, for row 2, its value is 3. So we're going to go back here and put 3. All right, now let's go and look at, I'm going to back out so we can see it. And let's look at where this occurs. And if you, again, these are estimates, but that's 3.45. 3.45. So we go back here, and what happened to my mouse? Okay. So this is 3.45 where we get our period 4, and I hope my map works. Hope I don't have to calculate it again. Trying to zoom out. There we go. So we're going to try to find this place right here. And we'll use one of these points. And that is 3.544. So period 8 appears at row equals 3.544. Okay, so we should be able to calculate that now. So this should be 3.544 minus 3.45 divided by 3.45 minus 3. So let's calculate that and see what it says. All right, so, and I'm gonna say, let's just call it Fn equals, well, let's do this. I'm gonna say R, first let's start with R. I'm gonna say R2 equals 3. Wait a minute, I didn't do that right. R2 equals 3. I'm going to say R4 equals 3.45. And R8 equals 3.544. And now I'll say Fn is equal to R, I'll use my parentheses because I know I'm going to need them. R8 minus R4 divided by R4 minus R2. So the estimated number we have is 0.2089. Now, first of all, let's make sure I did all that right. So that's that one minus that one over this one minus that one. Let me just try something. I want to make sure I have this, because it could be going the other way with the period. So let me do this first. Let me see what 1 over Fn is. Yeah, I think I might have it reversed as far as the sequence numbers are concerned, because the 1 over the value is actually closer to the actual estimated. So this might actually be the higher periods, or the lower period numbers, and that actually be the higher ones. I'll check on that. But as you can see, this number 4.78 is very close to so our Feigenbaum number we found, and I'll check on the sequence and values of this, but looks like about 4.7. What I have? 4.7. Yes, 4.79, which is, an estimate of what it should be, around 4.669. But again, that's a limit, and you would go further and further and further in to get more and more exact points. So in any case, this actually works out pretty well. All right, now one more thing I want to try to cover in this, and then we'll end it there, is this Lyapunov exponent. And I want to see if we can't, do a similar thing, but then we're going to use a time series to try to calculate the Lyapunov exponent. So let me just change this slide number, because I thought it was already changed. All right. So what happens here is in certain sections of your map, you can determine how much it spreads. Now, you have these 3 points that are very close to each other. The difference between them is a thousandth of a point, but between this point, and this point. So these 3 starting points are very close to each other. Then you iterate the map, in this case, 10 times into the future. You can do it how many you want to, but 10 times in the future to see how different they are. And as you can see, they're no longer only separated by 1,000. You can see the difference there. And we're going to do that. So you take this initial point minus the next iterated point, and you calculate the difference between those, and you can get this exponent. So if you solve for this, and let's go here, you'll see that the Lyapunov exponent is equal to the log. I'll just say the log. It doesn't matter which log you use. Log of d sub n over d0, and I'm going to say over log 2, right? Since we're using the 2 exponent, that's how you would calculate it. Now, so what is this dn? Well, dn is the difference after the fact, and this is the difference, when you start. So what we're going to do is look at the time series and see if we can't figure out how we might do this. Okay, so here's the time sequence, right? Now, one thing I want you to notice before we go too much further, you see these points right here? This was calculated for rho equals 4. And as you can see right here around 0.75, it kind of gets stuck. Well, that's the fixed point, and it wants to try to stay there, but the little bit of error or change in the values starts to make it walk away from the fixed point, and it gets bigger and bigger. So as you can see, that is where we are. And that's what it does. It walks away. Now, if this was to exactly fall on 0.75, it would stay. But it doesn't. As you can see, I don't know if you can see these numbers, but that's 0.7503, and it's a little bit different, right? So that difference starts to make it move away from the fixed point. Just as you can kind of see with this, there's a fixed point, but what happens, a little bit of error makes it walk away, and that difference gets bigger and bigger until it completely moves away. Okay, so let's go back to this. Because what we're going to do is we're going to find a couple of points that are close together. All right? Now, here's the first point. Let's use this. So in this case, we're going to say our first point is I'll have to remember. I'm using these 3 over here. So let's start 0.991. So 0.991. Now what I'm going to do is go, so we'll call this point A, this will be point B. And so this is the initial point, and I'm going to go 10 points in the future. All right, so if I go back here again, I was right here, and this is 127. So if I go to point 137, oh, that's 36. So this is 137. So it's 0.020. Okay, so this is 0.020. All right, that's where that point ends up. So now we're going to go to another point that is close by x0, but not exactly, right? So let's go back here. We were here. Let's use this one. And that's at number 131, but this is 0.997. So this is 0.997. And what number did I say that was? That was 131. So this is 131. So now we're going to look at 141. Let's go look at 141 and see if we can't find out where that one lands. It's probably somewhere around here. That's 37. And so here's 141, 0.565. So 0.565. All right. So those are the 2 points. Now, the difference between so this is the difference you initially want to have, right? So this difference here is 0.006. If I take this point minus that point, now we're going to say, what is this point minus that point? And that looks like it's 0.545. So look how much the difference has grown. All right, so then the Lyapunov exponent should be equal to the log of, and let's say this, so it's 0.545 over 0.006 and over log 2. All right, and we're going to figure that out. Use our trusty MATLAB. This over so I can see the numbers. So we're going to say so our Lyapunov exponent is equal to log of 0.545 divided by 0.06 divided by log of 2. And in this case, that Lyapunov exponent is 6.5, which is high. It's not super large, but it's large, especially when it comes to logarithmic scale. So it's large and it's positive, which means that it is expanding. There's stretching going on. So remember, though, there has to be somewhere where you have a negative Lyapunov exponent so that it gets squeezed. So we have to figure out where that might be. But that's an example for another day. I can kind of put you to work on doing that, because now all you have to do is find different regions of this map can be found just by the values. So you could look for values that, if you wanted to, let's go here. If you wanted to look at this part of the map and see perhaps maybe there's some squeezing that happens here, just look for values that are, in the very high region. Well, we kind of just did that, right? So it's clearly not there. But over maybe perhaps here or maybe back here, things get squeezed. Because if you think about it, this ends up getting projected to the line and then over here. So where does the squeezing happen? So I'll leave you to kind of explore and investigate on your own, because if this map is going to stay bounded and not blow up, there's got to be a negative Lyapunov exponent somewhere along in the region of that map. So I'll leave it to you to find that. But this is how it works. So what we'll do next time, and I'm just going to give you a taste of what you need to do, because here's an example here are some examples of some three-dimensional flows. All right, this is the Lorenz attractor. I think we talked about that before. This is what the time series solutions of this three-dimensional set of differential equations, and these are time differentials, right? Dx dt, dy dt, dz dt. And these are the equations of motion, and one of those, x of t, looks like this, and the others look similar. Here's one that is an electrical circuit. And these equations, again, of motion tell you what's happening within each component, a part of this circuit. The voltage with respect to time across this capacitor, the voltage with respect to time across the emitter, this is across the collector, I should say, the collector of this transistor. This is the emitter of the transistor, the voltage there, and the current that flows through here, we call it I sub L, which is this inductor current, but it's the current that flows through here. That's all you need to know in order to know what's happening in this circuit. And here are the equations for it. But again, plotted in a state space that has the current, the voltage, and the collector. For the collector, the emitter, and the inductor current. That's all you need to know. So any point along this flow tells you what's happening in the circuit at that given time. And again, if you want to look at each of these time-independent waveforms, time-dependent waveforms, the current looks like that, the voltage looks like that, the other voltage looks like that. And we'll talk more about it. But what I wanted to just show you as well is that what you can do in order to take a three-dimensional set of equations and turn it into a system. Okay, a third-order differential equation. So let's say that, and again, we can use time derivatives. So let's just say y, you have this thing that says y triple dot, that's a third-order time derivative, plus b double dot plus c y dot equals plus dy let's just say is equal to a constant a. Say you have that. Now, just so you know, this y dot is dy dt, okay? That's how it's, and as you go higher, it's the second or third derivative. All right, so you started with that, and you wanted to put it into this three-dimensional set of equations. Well, you can start like this. You could say, all right, let's let u equal to y. We'll let v equal to y dot, and we'll let w equal to y double dot. Okay. So then you're basically then your three-dimensional set will be W dot. Well, first of all, let me just change this over. Let's make this a Y triple dot equals A minus B Y double dot minus C Y dot minus D Y. Oh, no dot. All right, that's the same thing as this right here. Okay? Now you can say that, remember, W dot then is going to be is Y double dot, so W dot, W is Y double dot, so W dot is going to be triple dot. So now you can say W dot is equal to A minus B times W minus C times V, that's a V, minus DU. And then you have, of course, V dot is equal to W, right? And U dot is equal to V. So this is your system. This is your new system, which results in U, V, and W, which you could then plot in a state space if you wanted to, say in a three-dimensional state space, and call it U, V, and W. And if you have something going on there, then you can see it flow, right? Like that. And this is just, basically equivalent to, this is like Y dot, and Y double dot. Okay? And it tells you everything that you need to know about the system. So this is a way to take a complicated third order ordinary differential equation and turn it into a system like this, and so that you could perhaps look at it in a three-dimensional space, and then you could begin to study some of the chaotic behavior if it has it. And that's what happens on these different things. All right, I'll leave it there. I've given you a lot to consider, a lot to think about. But this is something, that's why we're recording it, so that you can go back, you can rewind it, you can make sure what I'm saying, you can make sure that I'm not making mistakes. And, you can comment, and it can help you work through some of the problems I give you, homeworks you've given, things like that. MATLAB is a valuable tool. Get very familiar with it. And, just, again, have fun. But, you got to kind of grab the basics before you can even play around and ask more questions. There's more questions to be asked and more answers to be had about all of this science and space around chaotic dynamics. It's a lot, and there have been tons and tons of publications and papers and books and movies and everything else, but no one still has all the answers. But I have the suspicion that this is how nature does its business, and we are kind of getting some investigation into it. All right, so I'm going to leave it right there. I look forward for your questions and all that stuff as we go forward. Take care.